So every rack system, every semantic search bar, every recommendation feed leans on the same hidden engine, a vector database. So what it does is it answers a question that sounds impossible at scale. So let's say you are given a query, you have to find out the most similar items out of millions in milliseconds. Not the exact matches, the closest in the meaning. So over the next few minutes, we open that engine up, how meaning becomes geometry, why brute force breaks down, and the clever index structures such as HNSW and inverted files that make billion scale search feel instant. So it all starts with what you call an embeddings. So what are actually embeddings? A model turns any piece of data, text, an image, a product into a vector, a long list of numbers, often hundreds of or thousands of them. So the trick is that meaning becomes position in a space. Things that are similar land close together in this high dimensional space, even with no words in common. So what a vector database stores is millions of these vectors and does one job extremely well. So if you given a new query a new query as a vector, it find its nearest neighbors. Everything else, the indexes, the math, the trade-offs exist to make that one operation fast and cheap at scale. So that's the whole idea of how a vector database working. So to find the nearest neighbors, like once you have given a query in a vector format into the vector database, to find that nearest neighbor, you need to define how much is this actual near. So there are a few common measures. So what you can do is you can do Euclidean distance is the straight line gap between these 2 points. So dot product multiplies and sums up the components, dividing vectors that are both aligned and large. And the other thing is cosine similarity, which measures only the angle between vectors, ignoring their length, which is why it is the default for text. So a short note and a long article about the same topic always points the same way. So most embedding models are tuned for this one specific measure. So you match the database metric to the model. Pick the wrong one and your results quietly get worse. So the obvious approach in all of this is brute forcing, sometimes called flat index. Compare the query against every single stored vector, sort by distance, and then return the top few. It is simple and perfectly accurate for a few thousand vectors, but when it scales, the problem also scales. Every query touches the entire database. So 10 million vectors with thousands of dimensions each means billions of multiplications per search. At that size, every query takes too long and burns too much compute. Accuracy is not the issue, but speed is. To go faster, you have to stop looking at everything, which means giving up perfect accuracy on purpose. So this is the central bargain of what you call vector search. What you do is approximate nearest neighbor or ANN. So instead of guaranteeing the exact closest matches, you accept results that are almost always right in exchange for being orders of magnitude much faster. What you're doing is you trade a tiny bit of accuracy for an enormous speed up. The quality of an ANN index is measured by recall. Of the true nearest neighbors, what fraction did it actually find? That's what a recall is. So a good index hits well over 90% recall while searching a tiny slice of the data. Every index we look at next is just a different clever way to skip most of the database while still landing on the right neighbors. So the most popular index today is what you call HNSW, hierarchical navigable small world. So picture a graph where each vector connects to its near neighbors and then stack that graph in layers. So the top layer is sparse with long range links like a highway map, and then the lower layers get denser like local inside streets. A search starts at the top, greedily hopes toward the query along the highways, then drops down a level and refines again and again until it is walking the local neighborhood around the answer. So you reach the right region in a handful of hops instead of scanning millions of points. It is fast and high recall at the cost of more memory for storing all those links. A different strategy is the inverted file index (IVF). First, what you do is you cluster all these vectors into groups, each with a center point during a training step. Then, to search, compare the query only to the cluster centers. Pick the few closest clusters and search inside just those. So here you ignore the vast majority of the data that lives in faraway clusters. A setting controls how many clusters you probe on. More clusters means higher recall but slower search. Fewer means the opposite of it. So IVF uses less memory than HNSW and shines on very large datasets, though it needs that upfront training step and a good number of clusters to work well. You have to figure that number out yourself. At scale, the vectors themselves become the cost. So consider the scenario: millions of high dimensional vectors in full precision eat enormous memory. So what you do is you apply quantization on it. So quantization actually shrinks them. So you can actually do scalar quantization, which stores each number in fewer bits, say 8 instead of 32. So product quantization even goes further. It splits each vector into chunks, builds a small codebook of common patterns per chunk, and stores just the codebook IDs, compressing vectors many times over. The catch over here is the precision loss. So distances become approximate twice over, once from the index and once from the compression. A common pattern is to search fast on compressed vectors, then re-rank the top candidates using the full precision originals to recover accuracy. So real queries are rarely pure similarity. You want the nearest vectors that also match conditions. Let's say for this user, in stock, written in this year. So that is what you do metadata filtering. But it is trickier than it sounds, because a filter can remove most of the candidates the index wanted to return. So good vector databases blend the filter into the search rather than bolting it on after. Many systems also run something called hybrid search, combining vector similarity with classic keyword matching, then merging the two rankings so exact terms like a product code are not lost to fuzzy meaning. The best retrieval is usually semantic plus keyword plus filters all working together. So that is the engine behind semantic search. So embeddings turn your data into points whose closeness is meaning. You measure that closeness with cosine, dot product, or Euclidean distance. Brute force is accurate but scales linearly, so you switch to approximate nearest neighbor, trading a little accuracy for huge speed. HNSW navigates a layered graph, IVF searches only the nearest clusters, and quantization compresses the vectors to fit in memory. Add filters and keyword hybrid search, and you have a system that finds the right needle in millions in milliseconds. No magic, just geometry and some very clever indexes. I hope this have answered some of the questions regarding how a vector DB works. If you have any questions, let me know in the comments.